How do you apply Jacobian and DH parameters in robot kinematics? Imagine trying to control a robotic arm so it moves smoothly and precisely. To do that, you need a way to understand how each joint affects the end of the arm. That's where the Jacobian matrix and Denavit Hartenberg parameters come into play. They are essential tools in robot kinematics, especially when working with control systems and automation. First, the Denavit Hartenberg parameters help us describe the robot's structure. Think of them as a set of numbers for each link: how long the link is, how much it twists, how far it is offset, and the joint angle. These parameters let us create a series of transformation matrices that tell us exactly where each part of the robot is in space. This makes it easier to solve the forward kinematics problem, which is figuring out where the robot's end effector is based on the joint positions. Once we have these transformation matrices, we can determine the position and orientation of the robot's end effector. But in real-world applications, we often need to control how fast the end effector moves or how it reacts to forces. That's when the Jacobian matrix becomes useful. It links the joint velocities to the velocity of the end effector. In simple terms, it tells us how small changes in joint angles or displacements will affect the position and orientation of the robot's hand or tool. From an electrical engineering perspective, the Jacobian is vital for controlling robotic movements. It allows us to calculate the end effector's velocity from known joint velocities. Conversely, if we want the robot to move at a certain speed, we can invert or pseudo-invert the Jacobian to find the necessary joint velocities. This is especially important in trajectory planning and dynamic control. Additionally, the Jacobian helps us figure out the joint torques needed to produce specific forces or movements at the end effector. By using the transpose of the Jacobian, we can relate forces applied at the end of the robot to the motor inputs. It also helps identify singularities, which are positions where the robot loses some degrees of freedom, making control difficult or impossible. Recognizing these points allows us to adjust the robot's path to avoid problems. Practically, you start by using the DH parameters to build the forward kinematic model. Then, differentiate the equations to find the Jacobian matrix, which includes both linear and angular velocity components. During operation, you monitor the Jacobian's determinant or singular values to detect potential issues. When controlling the robot, you use the Jacobian to convert desired end effector velocities into joint velocities or forces. This process ensures smooth, accurate, and safe movements. In summary, the DH parameters give us a clear picture of the robot's geometry, making it straightforward to calculate where each part is. The Jacobian then connects these positions to how the robot moves and reacts dynamically. Together, they form the backbone of robot control systems, enabling precise and reliable automation in various applications.